Hello everybody, my name is Ethan. Welcome back to the channel where today we are going to continue our machine learning in Python course here, and we are going to be introducing ourselves to the topic of logistic regression. In the previous two videos we learned about linear regression, simple linear regression that is, and then multi-linear regression. So through this chapter, we're going to hope to do some interesting stuff. I'm a little familiar with logistic regression, but hopefully we each can learn something new today. So I'll start off right away, stop wasting your time, and we'll start with the introduction here. When an email lands in your inbox, how does your email service know whether it's real or spam? This evaluation is made billions of times per day, and one possible method is logistic regression. Logistic regression is a supervised machine learning algorithm that predicts the probability ranging from 0 to 1 of a data point belonging to a specific category or class. These probabilities can then be assigned or used to assign, classify. These probabilities can then be used to assign or classify observations to the more probable group. For example, we could use a logistic regression model to predict the probability that an incoming email is spam. If that probability is greater than 0.5, we could automatically send it to a spam folder. This is called binary classification because there are only two groups, spam or not spam. What are some other examples of problems that we could use, that we could solve using logistic regression? Disease identification is a tumor. I'm not a doctor, so I don't know that word. Customer conversion, will a customer arriving on a sign-up page enroll in a service? In this lesson, you will see how to perform logistic regression and use it to make predictions. If you are unfamiliar with linear regression, we recommend you review it before proceeding. Otherwise, let's dive in. So it's saying if you don't know what linear regression is, review it. Hey, I have a linear regression video, so if you want to go look at that, please be sure to go do that. Okay, Codecademy's University Data Science Department is interested in creating a model to predict whether or not a student will pass a final exam of its introductory machine learning course. They plan to accomplish this by building logistic regression models that predicts the probability of passing based on the number of hours a student reports studying. Run the code in script.py to plot the data. 0 indicates that a student failed the exam and 1 indicates a student passed the exam. How many hours does a student need to pass the exam? So if we run this, you'll see that once we start to hit that 10-hour mark, it's more likely that they will pass the course. Linear regression approach. With the data from Codecademy University, we want to predict whether each student will pass their final exam. Recall that in linear regression, we fit a line to the following form of data. This is, of course, multiple linear regression. Just simple linear regression or just one variable linear regression would show that it's mx or y is equal to mx plus b. But in this case, we have b. Oh, interesting. B is the intercept. Oh, and it just has b as also the coefficients, which is interesting that they don't use m as the variable there, because typically m dictates the coefficient or slope of the predictors. Okay, for our data, y is a binary value either equal to 1 or 0, and we only have one predictor, x1, number of hours study. Below, we fitted a regression line to our model and plotted the results. The best fit line is in red, so you can see it right here. There's the best fit line. We see that the linear model does not fit the data well. Our goal is to predict whether a student passes or fails. However, a best fit line allows for predictions between negative and positive infinity. Obviously, that doesn't make a whole lot of sense. We've provided you with the code to train a linear regression model on the Codecademy University data and plot a regression line. That's this right here. Run the code and observe the plot. Expand the plot to full screen for a larger view. Using the regression line, estimate the predicted hours given the line for students who study 0 hours, 1 hour, or 10 hours, and 30 hours respectively. Save the results to slacker, average, and studious. How would you use these three numerical outcomes to determine whether a student is predicted to pass or fail? Can you think of a threshold you might use? So we have a couple of interesting things here. First, it wants to just define the three variables here. It says estimate the predicted outcomes given by the line. So if we look at the line, we have 0 hours studied here. If we go up to the line, it's going to be a negative outcome, right? We're looking at a negative outcome. So if we go up to 10, we may see a 50-50 outcome. And then finally, when we go to 30, we can't really go above 1. So we're going to say that Slacker has a 0.01% chance. The predicted outcome is that Slacker would be equal to 0.01, average would be equal to 0.5, and then Studious is equal to, I'm going to do 0.99, just because it's not ever going to ever be 100% chance that you pass the class, right? Value for Slacker is incorrect. Let's then just try this, and I assume it's going to be something like that, maybe. Find 1 hour, even though it says study 0 hour. The x-axis. Yep. So what does it actually put here? Interesting. So it wanted me to not kind of go past it here. So negative 0.2, 50, and then 1.75 is what I believe 30 ends up going to up here, yeah. Which obviously don't make sense for the idea of this graph. What does negative 0.2 mean? Logistic regression. We saw that the predicted outcomes from a linear regression model from negative to positive infinity. These predictions don't really make sense for a classification problem. Step in logistic regression. To build a logistic regression model, we apply a logit link function to the left-hand side of our linear regression function. Remember, the equation for a linear model looks like this. We apply the logit function, and we get the following. ln of y over 1 minus y is equal to the linear regression model. For the Codecademy University example, this means that we are fitting the curve shown below to our data instead of a line like in linear regression. Notice that the red line stays between 0 and 1 on the y-axis. Now it makes sense to interpret this value as the probability of a group membership, whereas that would have been more nonsensical for regular linear regression. Note this is a pretty nifty trick for adapting a linear regression model to solve classification problems. There are many other kinds of link functions that we can use for different adaptations. We've provided the code to build a logistic regression model on the Codecademy University data and plot the fitted curve. Take a look at the plot. Expand the plot to full screen for a larger view. Using this curve, estimate the probability that a student who studied for 5 hours will pass the exam, and save it save the result as 5-hour studier. So if we go up here, we'll notice that if a 5-hour studier, it's looking like it's in between 0 and 0.2. So if I had to say, I'm going to say 5-hour studier is going to equal 0.1, or just about a 10% chance of passing the class if they study for 5 hours. And that is correct. Log odds. So far we've learned that the equation for a logistic regression model looks like this. ln of p over 1 minus p is equal to the linear regression model. Note that we've replaced y with the letter p because we're going to interpret it as a probability, the probability of a student passing the exam. The whole left-hand side of the equation is called the log odds because it is the natural logarithm of odds p over 1 minus p. The right-hand side of this equation looks exactly like a linear regression model. In order to understand how this link function works, let's dive a little bit deeper into the interpretation of log odds a little more. The odds of an event occurring are p over 1 minus p or the probability of the event occurring over the probability of it not occurring. Suppose that the probability a student passes the exam is 0.7 or 70%. That means that the probability of failing is 30%. Thus, the odds of passing are 2 over 3.3. This means that the student is 2.33 times more likely to pass than fail. Odds can only be a positive number. When we take the natural log of odds, the log odds, we transform the odds from a positive value to a number between negative and positive infinity, which is exactly what we need. The logic function, or log odds, transforms a probability, which is a number between 0 and 1, into a continuous value that can be positive or negative. Suppose that there's a 40% possibility of rain today. Calculate the odds of rain and save it to odds of rain. Note that the odds are less than 1 because the probability of rain is less than 0.5. Feel free to print it if we want. So we can print odds of rain is equal to 0.4 divided by 0.6. And then we can print odds of rain. So we see that there is going to be, the chance that if we were to flip this, it's 2/3 more is likely to rain than not rain. Use the odds that you calculated above, the log odds of rain, and save it to log odds of rain. We're going to have to use np.log, and then we'll take odds of rain. So now we see that it's a -4 when we take the log, or negative 0.4%. Suppose, not percent, negative 0.4 or about 40%. Suppose that there is a 90% probability that my train to work arrives on time. Calculate the odds of my train being on time and save it to odds on time. So odds on time is equal to 0.9 divided by 0.1. Use the odds that you calculated above to calculate the log odds of an on-train time and save it to log odds on train. Note that the log odds are positive because the probability of an on-time train was greater than 0.5. So we'll do log odds on time is equal to numpy.log to the odds on is it going to be the same number? Did I do it right? I think I did it right. Oh, log odds on. There we go. That makes sense. Sigmoid function. Let's return to the logistic regression equation and demonstrate how this works by fitting a model in sklearn. The equation is, of course, natural log of p over 1 minus p is equal to the linear regression model. Suppose that we want to fit a model that predicts whether a visitor to a website will make a purchase. We use a number of minutes they spend on a site as a predictor. The following code fits the model. So, logistic regression model is equal to fit, min on site, and purchase. Next, just like linear regression, you can use the right-hand side of our regression equation to make predictions of our original data points as follows. If we do log odds is equal to model.intercept plus model.coefficient times minute on site, we'll see all of the different outputs we have. Notice that these predictions range from negative to positive infinity. These are log odds. In other words, for the first data point, we have this, and we can turn log odds into a probability as follows. In Python, we can do this simultaneously for all the data points using numpy loaded in as np.exponent, and we do that. The calculation we did just required us to use something called the sigmoid function, which is the inverse of the logit function. The sigmoid function produces the S-shaped curve we saw previously, right here. In the workspace, we fitted a logistic regression on the Codecademy University data and saved the intercept and coefficient on our study as intercept and coefficient respectively. For each student in this data set, use the intercept and coefficient to calculate the log odds of passing the exam, save the result to log odds. So it wants us to use this basically. So log odds is equal to model dot, or I guess we can do intercept plus coefficient times, and our data is hours studied. Now convert the predicted log odds for each student into a predicted probability of passing the exam. Save the predicted probabilities as predicted probabilities passing. So we can do that. It wants us to convert the predicted log odds, which is this right here, all of these, for each student into a predicted probability of passing the exam. This one's a little bit interesting. To convert log odds to probabilities, use the sigmoid function. np.exponent of log odds divided by 1 plus np.exponent of log. So we have it up here. It's this right here. Fitting a model in sklearn. Now that we've learned a little bit about how logistic regression works, let's fit a model using sklearn. To do this, we'll begin by importing the logistic regression model and creating a logistic regression object by just doing this. After creating the object, we need to fit our model on the data. We can accomplish this by using the .fit method, which takes two parameters, a matrix of features and a matrix of class labels, the outcome we are trying to predict. Now that the model is trained, we can access a few useful attributes. Model.coefficient is a vector of the model coefficients of each feature, and model.intercept is the intercept. The coefficients can be interpreted as follows: large positive coefficient, large negative coefficient, and then a coefficient of 0. One important note is that sklearn's logistic regression implementation requires the features to be standardized because regularization is implemented by default. We've pre-processed this data and split it into training and test sets as follows. Xtrain is the feature matrix containing standardized training data for hours studied and practice test scores. Ytrain contains the outcome variable for the training data, whether or not each student passed the final exam. Create a logistic regression and fit the logistic regression model here. So first create the object, and then we'll do cclr dot fit using xtrain and ytrain. And we'll print out the coefficients and intercept of the model. So we'll do that by doing print cclr.coef underscore. And we'll also print out cc underscore dot lr dot intercept. And there they are. Predictions in sklearn. Using a trained model, we can predict whether new data points belong to the positive class, the group labeled as 1. Using the .predict method, the input is a matrix of features and the output is a vector of predicted labels, 1 or 0. Print model.predict features, sample output 0, 1, 1, 0, 0. If we're more interested in the predicted probability of a group membership, we can use the .predict proba or prob A method, and the input to predict underscore prob A is also a matrix of features, and the output is an array of probabilities ranging from 0 to 1. By default, predict prob A returns the probability of a class membership for both possible groups. In the example code above, we've only printed out the probability of belonging to the positive class. Note that data points with predicted probabilities get greater than 0.5. The second and third data points in this example were classified as 1s by the predict method. This is a process known as thresholding. As we can see here, sklearn sets the default classification threshold probability as 0.5. So in the workspace, we fit the same logistic regression model on the Codecademy U training data. I've also created xtest and ytest, which contain the testing data. Use the .predict method to predict whether the students in the data set will pass the final exam, then print out the resulting vector of predictions. So we'll do that. They've done this. They've done a list for us, which is extremely nice. We can do this by using the .predict method, or we can new data points and other positive. It's just using the .predict method to predict. So we can do that by doing print cc underscore lr dot predict, and then it wants us, the input is a matrix of features and the output is a vector of protected labels. So what are the features that it wants me to throw in there? Just xtest. Okay. Zero, 1, 0, 1, 1. Now use the predict prob A method to calculate the predicted probabilities that each student in the dataset will pass the exam. Print cc underscore lr dot predict prob A of x test. There is that. Print out the y-test to see whether the students in the test dataset actually passed the exam. Did the model make accurate predictions? Looking at probabilities, do the misclassifications make sense? So when we print this out, we'll see a lot of interesting data here. You should see that the fourth data point was incorrectly classified as having passed the exam. However, the predicted probability for this was only 57.7, which is much lower than the others who were correctly predicted to pass the exam. Boom and boom. Classification thresholding. As we've seen, logistic regression is used to predict the probability of group membership. Once we have this probability, we need to make a decision about what class a data point belongs to. This is where classification threshold comes in. The default threshold for sklearn is 0.5. If the predicted probability of an observation belonging to the positive class is greater than or equal to the threshold of 0.5, the data point is assigned to the positive class. We can choose to change the threshold of a classification based on the use case for our model. For example, if we're creating a logistic regression model that classifies whether or not an individual has cancer, we may want to be more sensitive to the positive class. We want to tell someone they don't have cancer when they actually do. In order to ensure that most patients with cancer are identified, we can move to the classification threshold down to 0.3 or 0.4, increasing the sensitivity of our model to predicting a positive cancer classification. While this might result in more overall misclassifications, we are now missing fewer of the cases we are trying to detect actual cancer patients. There we go. In the workspace, we fit the same logistic regression model on the Codecademy U training data. We've also printed the predicted classes and true classes for the test data. Take a look at the predicted probability of passing the exam for the misclassified data point. The predict method uses a default threshold of 0.5 for predicting group membership. For this example, we could correctly classify all 5 data points in the set using a different threshold. Set the value of alternative threshold to any value that would accomplish this. So if we go here, wants us to reset the value of alternative threshold, which if we do alternative threshold, we're going to lower it down to 0.3. Let's see if that ends up working. It's telling me it's not in the correct range. Does it use alternative threshold anywhere, actually, though? Set a value to any... What does it actually say? 0.6. Note, any value between it will work. Wish they did a little bit better job of this one right here. We can continue. Confusion matrix. When we fit a machine learning model, we need some way to evaluate it. Often we do this by splitting our data into training and test data sets. We use the training data set to fit the model, and then we use the test to see how well the model performs with the new data. As a first step, data scientists often look at a confusion matrix, which shows the number of true positives, false positives, true negatives, and false negatives. For example, suppose that a true and predicted class for a logistic regression model are the true and the predicted. We can create a confusion matrix as follows. We go to sklearn.metrics and import confusion matrix, and then we print out a confusion matrix. This output tells us there are 3 true negatives, 1 false negative, 4 true positives, and 2 true positives. Ideally, we want the numbers on the main diagonal, in this case 3 and 4, which are true negatives and true positives, respectively, to be large as possible. In the workspace, we fit the same logistic regression model of the Codecademy U training data and made predictions for the test. Y test contains the true classes and Y prediction contains the predicted classes. Create and print a confusion matrix for this data. How many incorrect classifications were there? So it wants us to implement the confusion matrix. If we print the confusion matrix we'll first put our Y data, that is Y test data, and then we'll have our Y predicted data. And when we print this out, we should see this variable here, which means we had 2 true positives, I want to say it was. So true negative. The negatives are up top, I would say then, right? 1 false negative. Nope. 4 true positives and 2 false. So this is a false negative and this is a false positive. And then these are the two true. So in this case, we have a true negative, a false positive, 0 false negatives, and 2 true positives. Accuracy, recall, precision, F1 score. Once we have a confusion matrix, there are a few different statistics we can use to summarize the 4 values in the matrix. These include accuracy, precision, recall, and F1 score. We won't go into much detail about these metrics here, but a quick summary is shown below. T is equal to true, F is equal to false, P is equal to positive, N is equal to negative. For all these metrics, a value closer to 1 is better, and a value closer to 0 is worse. So here's the accuracy, precision, recall, F1 score. And in sklearn, we can calculate these metrics as follows. We can just actually import them and see their actual output. In the workspace, we've fit the same logistic regression model in the Codecademy U training data and made predictions for the test data. Y predictions contains the predicted class and Y test contains the true classes. Also note that we've changed the train test split by using different value for the random state parameter. Making the confusion matrix different from the one you saw in the previous exercise, calculate the accuracy for the model and print it out. So if we do that, we'll just print accuracy score of Y test and Y predicted. Looks like we got an accuracy score of about 80%. And calculate the F1 score for the model and print it out. If we do that, we can find if we do print F1 underscore score with the values of, again, that Y test and Y predicted. All right, review. Congratulations, you just learned how logistic regression model works and how to fit one to a data set. Here are some of the things you learned. Logistic regression is used to perform binary classification. Logistic regression is an extension of linear regression where we use the logic link function to fit a sigmoid curve to the data rather than a line. We can use the coefficients from a logistic regression model to estimate the log odds that a data point belongs to a positive class, and then we can transform the log odds to a probability. The coefficients of a logistic regression model can be used to estimate relative feature importance. A classification threshold is used to determine the probabilistic cutoff of where a data sample is classified as belonging to a positive or negative class. The cutoff in sklearn is 0.5. And we can evaluate the logistic regression model using a confusion matrix or summary statistics such as accuracy, precision, recall, and F1 score. And we can do something on Kaggle, but we're going to click up next. Let's take the quiz. You run a logistic regression model and compare the predicted classifications with the test data set and find the following results. True positive 25, true negative 36, false positive 5, false negative 4. What are the accuracy, precision, and recall metrics of this data? You'd have to remember by heart the formulas for this, and I just don't think I'm going to ever recall these. I'm going to go with this one, and the correct answer was the second one. And it tells us right here, you can calculate them out if you want to. I'm not going to do that. I'm not going to focus myself on something like that. Logistic regression differs from linear regression because the output of a logistic regression model ranges from negative infinity to positive infinity. That's true. It's the opposite. Sorry about that. Logistic regression model that predicts if a credit card transaction is fraudulent is trained on the data set with 4 features. The model's coefficients for each feature are given below. Which feature has the greatest impact on chart's classification and which feature has the least impact? So the most impact is going to be previous purchase and the least impact is going to be international. So least impact international, greatest impact previous purchase, right? You run a logistic regression model and compare the predicted classifications with your test data set and find the following results. True positive 25, true negative 36, false positive 5, false negative 4. What be the confusion matrix look like? Oh my goodness. Okay, so negatives were on the left. So true and then bottom right would be 25. Top right would be 5. So this should be 5. It should be 36, 5, 4, 25. This one right here. Glad I actually looked at that. You have been studying public transportation in your area for the last few months and have noticed that buses have been late 35% of the time at your stop. Calculate the odds and log odds that a bus will be late. So odds is 35% divided by 35% divided by or 0.35 divided by 0.65. It looks like about 53%, 54. Yep. And then the log odds, since it's over 54%, it's going to be positive. Nope. Even though it said it was over 50%. I suppose if we probably wrapped that in a log. I should have just taken the time to do that, but it's fine. We're going to actually probably have to retake this test, which is annoying. But which of the following describes the output of a logistic regression? Either it's 0 or 1. Yeah, logistic regression will evaluate a probability of event occurrence and will compare that against the decision threshold to give a prediction. Which feature can we apply to linear regression to solve classification problems? The logic link. You have a logistic regression model predicting if a customer will make a purchase or not after running the .predict method. You see the following output. Which of the following matrices could be the result from running a .predict probe on the same data set? Assume the standard classification. Again, it's going to want me to do some sort of math, which is a little annoying because I'm not going to sit here and do math for 45 minutes. So if I'm looking at it here, 1, 0, nope, 1, 0, nope, 1, 0, nope, 1, this one. Based on a threshold of 0.5, the resulting predictions for this matrix would be 0, 1, or 0, or 1, 0, 0, 1, 1. I'm so good. Which of the following plots shows a sigmoid function? C, right? Which of the following circumstances would be the best candidate for decreasing the standard classification? The cancer one. Let's see if we have to retake it. We don't. So we got a couple wrong there, but that's okay. So now we have a test, or not a test, but a project. Predict credit card fraud. Credit card fraud is one of the leading causes of identity theft around the world. In 2018 alone, over $24 billion were stolen through fraudulent credit card transactions. Financial institutions employ a wide variety of different techniques to prevent fraud, one of the most common being logistic regression. In this project, you are a data scientist working for a credit card company. You have access to a data set based on a synthetic financial data set that represents a typical set of credit card transactions. Transactions.csv is the original data set containing over 200,000 transactions. For starters, we're going to be working with a small portion of the data set called transactions_modified.csv, which contains 1,000 of those 200,000 transactions. Your task is use logic regression and create a predictive model to determine if a transaction is fraudulent or not. Note that solution.py is a file loaded for you on the workspace, which contains solution code for this project. We highly recommend you complete the project on your own without checking the solution, but feel free if you get stuck. All right. The file transactions modified contains over 1,000 simulated credit card transactions. Let's begin loading it by using the pandas data frame and take a peek at it using info and head. How many transactions are fraudulent? Print your answer. Oh, it already has read in the data here. If I save this and run it, what ends up happening? We end up seeing is fraud is a null value. If we scroll over here, it's a 0 or 1 if it's a fraud. So that's kind of an idea that you may want to be a logistic model. How many? There are 1,000 rows if I had to assume. To examine how many rows there are and what data types there are. I see. So in this data set, it seems that there are 282 fraud detected stuff. Looking at the data set combined with our knowledge of credit card transactions in general, we can see that there are a few interesting columns to look at. We know that the amount of a given transaction is going to be important. Create summary statistics for this column. What does this distribution look like? Okay, sorry about that. If we do transactions.mean, looking at specifically the column amount, there's probably just a function for summary statistics. Yep, the describe function, of course. Who would forget that one? If we do this and then wrap it in a print statement, and I am going to quickly save myself some stuff. So when we describe it here, I'm also going to print or hide the other stuff here just so that it's not clogged and I can just see. Okay, so the summary statistics on the amount, we can see that the mean amount is just shy of $540,000. Standard deviation is a lot, to be honest. It's over $1 million. The minimum value of a transaction was 0, and the max value was, let's count this up, 1, 2, 3, 1, 2, 3, 1, 2. So should have counted that from the back. 1, 2, 3, 1,000, 10 million. There we go. Okay. So, what does the distribution look like? We have a lot of information about the type of transaction we're looking at. Let's create a new column called is payment that assigns a 1 when type is payment or debit and 0 otherwise. So we can do this by doing transactions and creating it saying is payment. Let's actually see what they want us to do is equal to, a new value. Yeah. You can filter a data frame for specific values like this. So it wants me, I'm just gonna do this. Is when this when type is equal to we'd want to use this and say that's equal to 1 when it's a payment. I want to maybe use an if statement here. I do want to see what the solution does. Is in. Okay. Transactions payment. So that's what they do. So we create the is payment field by just doing transactions of is payment, and we'll just set everything equal to 0 to start, and then after if trans, we'll edit it by doing transactions is payment where transactions of type is equal to payment or transactions of type is equal to debit. Set this equal to 1. And is payment getting quite a few errors here. When I look at the solution here, what is it telling me? It wants to do dot is in. Just don't understand why I couldn't do is equal to this or equal to this. We'll use the is in method for right now and see if that helps us out. That ends up working for us. Similarly, create a column called isMovement, which will capture if money moved out of the origin account. This column will have a value of 1 when the type is either cash out or transfer, and 0 otherwise. So we'll do something very similar. We'll do transactions of isMovement, set it equal to 0, and then we'll edit it if transactions is movement, and we'll do this now where we do transactions of type. Dot is in. Cool. With financial fraud, another key factor to investigate would be the difference in value between the origin and destination account. Our theory in this case being the destination accounts with significantly different value could be suspect of fraud. Let's create a column called account diff with the absolute difference of the old balance org and old balance destination columns. New column then called, so new column in transactions, it wants it to be called account diff. We're going to set that equal to the absolute difference, so we'll wrap that in an absolute value sign, and of the transactions of the old balance org column minus the transactions of old balance dest column. And of course, remember to do that. Looking good so far. Select and split the data. Before we can start training our model, we need to define our features and label our columns. Our label column in the dataset is the isFraud field. Create a variable called features, which will be an array consisting of the following features. Also create a variable called label with the column isFraud. So it wants me to create a variable called features. Which wants to be a numpy array. Before we can start training our model, we need to define our features and label columns. Our label column is in the data set is the isFraud field. Create variables called features, which will be an array consisting of the following fields. Also create a variable called label. Okay, I'm gonna just check the solution just because I feel like it. That looks good. And it just wants me to do that, not actually use dot array. I should not have opened up transactions modified. That was a wrong move. Oh no. It's gonna crash, you guys. Okay. We're good. Don't open up these CSVs, whatever you do. Okay, so it doesn't want me to do this type of an array. It just wants me to do a transactions and then a double list here with the values of amount. Is payment. Is movement. And finally, account diff. All right, split the data set into training and test using sklearn's trains test split method. We'll use the training set to test the model. Okay, so we're going to split the data set. So let's check if it's imported. It is imported as train test split. So we'll do that by doing train test split. And we'll do, I know we're going to have a couple of features here. I know it takes 4 variables, but let's check what it takes. Oh, we have to capture our stuff in x train, x test, y train, y test is equal to train test split. And inside train test split, I know we do x and y. There's going to be some value of x, some value of y, and then train something. It's train value. Train split is equal to 0.7, meaning test split is equal to 0.3. Now I know I got this wrong, so let's take a peek at the solution and see how they did it. Test size is what we wanted. Test size. Oh, no. This is bad. Okay. My God. Wish I could move that to like the end or something. So I guess you don't need to specify train split. If you have one of them, you kind of understand that you have the other. So we can do features, and label. Cool. Test hot split size. Using, let's go on to normalize the data. Since sklearn's logistic regression implementation uses regularization, we need to scale our feature data. Create a standard scalar object, .fist transform it on the training features, and transform the test features. So we'll start by creating a standard scalar object. Then we'll use fit transform on it by doing scalar.fit transform on the training features, which means x train and y train, and transform the test features. See if I did this right. Survey says it's just, I think the easiest way to do this is to go into the solution and see where I'm fucking up. Scalar is equal to standard scalar. You just do it on that and you save it to itself. Create a logistic regression model with sklearn and fit on the training data, fitting the model from the best coefficients of our selected feature so it can accurately predict. We'll start with the default threshold of 0.5. First, we'll have to add in logistic regression object. I'm going to call it logistic regression object, or RLO, is equal to logistic regression. And then we'll do LRO dot fit, and we'll fit the X the training data, so train to Y train. All seems so good so far. I'm gonna just scroll down and make sure that I'm not messing everything up. Yep. He just said it was, he just put the variables model, or they did. And finally, we're gonna run the model score method on the training data and print the training score. Scoring the model on the training data will process the training data through the trained model and predict which translations are fraudulent. The score returned is the percentage of correct classifications or the accuracy. So we'll score it by doing RLO.score, and it wants me to print that value out, so I'll wrap it in parentheses and do something like that. We want to actually put some very helpful error there. 84%, which is pretty good. Run the model score method on the test data and print the test score. So we'll do that again. Print lro.score x test y test. Bit better than the actual training. So that's actually pretty good. Print the coefficients for our model to see how each feature for prediction, which feature was most important, least important. Print the model coefficients. So we'll do that by doing print rlo dot coefficients. It's asking us which feature is most important, which one is least important. It looks like of the 4, the least important was number 2, which when we go back up is the is payment one. All the other ones were at least above a score of a 1.2. So it looks like the is payment was the least. Predict with the model. Let's use our model to process more transactions that have gone through our systems. There are 3 NumPy arrays preloaded in the workspace with information on sample transactions under new transaction data. Make a 4th array called your transaction and add any transaction information you'd like. Make sure to enter all values with floats with a period or a decimal point. So it wants me to go up here, right here. Oh. Sorry, your transaction. Set it equal to the np.array. That is equal to, we'll start with something that's similar. So we'll do 431,600 552 dot 1.1, we'll say that this is 1.0 dot 0.0 dot 13,101 dot 176. Fine with me. Combine the new transactions and your transactions into a single NumPy array called sample transactions. Combining stuff into a new array. What's the formula for that? Stacky. Double wrapped, because why not? Since our logistic regression model was trained on scaled feature data, we must also scale the feature data we are making predictions on. Use standard scalar object created earlier, apply its transform method to simple transactions, and save the result to sample transactions. So sample transactions is equal to the standard scalar object created before, which was scalar dot transform, and we'll put in sample transactions. Predict method on sample transactions. So now we can do it by putting our model to the test. I believe I called it linear regression object dot predict on the new sample transactions. I see it wants me to do predict prob a of sample transactions and print the results by wrapping it right here and printing it out. gives us a lot of good information here. The first column is the probability of a transaction not being fraudulent. The second column is the probability of a transaction being fraudulent, which was calculated by our model to make the final classification decision. I assume we did everything correct here. Yeah. Oh, we wanted to actually do dot predict first, and then predict prob A. I skipped a bit of a step there. Cool. So we got zeros across the board, which means that we believe that none of the transactions we had were fraudulent. And then we have some interesting data here. We're a little less confident about the first data, but because we had that threshold of 0.5, we still say that it is safe and not fraudulent. Cool. All right, that's going to do it for today's video. We covered logistic regression. In the next video, we are going to be talking about the k nearest neighbors classifier. Is a classification algorithm. If you did enjoy the video, please be sure to leave a like and subscribe. I've been Ethan. Thank you very much, and I'll see you next time. Peace out.